Hello, in this video I'll be going over some partial differential equations via separation of variables. So in this video, this is an advanced calculus topic. So if you have a partial differential equation, it's basically an equation that's comprised of partial derivatives. So a partial derivative is when you differentiate a multivariable function with respect to one of the variables, and to differentiate that you just treat it as a constant. So I'll just give you an example. If you have a function of x and y, and it's equal to, let's say, x squared sine of y, and you wanted to find the partial derivative with respect to partial derivative of f with respect to x, you would just differentiate this function and treat y as a constant. So how would we do that? So differentiating this, x squared sine of y. Okay, so if y is a constant, then this sign here of this is just a constant too. So all we got to do is do the power rule here. So the partial derivative of f with respect to x is equal to 2x sine of y. Okay, so that's basically what partial derivative is in just basic terms. In this video, we're going to be basically solving partial differential equations, so equations that comprise of partial derivatives, and you're asked to find the function of the variables pretty much. So let's just have a go at this first one. So this is our first partial differential equation. So you have the partial derivative of f with respect to, let's say, x, plus the partial derivative of f with respect to, let's say, t. Okay, and that's equal to 0. So this is called a PDE, okay? And that stands for partial differential equation. Okay? Now, how do we solve something like this? Because we want to find a function of x and t that pretty much satisfies this equation. Now, how would we do that? So basically what you have to do to solve something like this is you have to make an assumption. So you have to assume that f of x and t is the product of a, let's say, function of x and a function of t. So the product means you have a function of x multiplied by a function of t. So you have to make that assumption in order to solve this via separation of variables. Now what do we do? Well, basically, we have an expression, just a general expression for how our function is going to look for two variables. So now we're just going to find a general expression for the corresponding derivatives. So how do we do that? So basically, we're going to differentiate this equation here with respect to x and with respect to t. So let's just do x. So the partial derivative of f with respect to x, you're going to differentiate this right-hand side with respect to x. So t is a constant. So when we differentiate this side here, u of x is just going to be u dash of x. So whatever the function of x here, it's going to be its derivative multiplied by g of t. Okay? So that's the partial derivative of f with respect to x. Now let's find the partial derivative of f with respect to t, because we have it up here in our PDE. So now we're just going to differentiate basically with respect to t. So x is now our constant, so the function of x doesn't change, but our g of t turns to g prime of t, so the derivative of g of t, okay? And pretty much all we do now is put this and this into our PDE up here, okay? So let's just rub that out now, and let's move our stuff to the side. So we have basically a general expression for our function and its corresponding derivatives. So let's just move, whoopsie daisy, let's just move all of this to the side and make that a bit smaller. Okay, so let's rewrite our PDE. So 2 partial derivative of f with respect to x plus partial derivative of f with respect to t is equal to 0. Partial derivative of f with respect to x is going to be 2 multiplied by u dash of x multiplied by g of t plus the partial derivative of f with respect to t, which is going to be u of x multiplied by g prime of t is equal to 0. And we can just simplify this, so u and gt. Now what we do now is basically get all of our functions, we separate our functions pretty much. So we get our functions of x on one side and our functions of t on the other. So we'll have left hand side, right hand side. As long as all of your x's are on one side and all your t's on the other, it doesn't matter where this is on the left hand side or this is on the right hand side, it could be either. Okay? As long as you have them separated. So how are we going to do this? Well, first off, I'm just going to move this term here to the other side. So I'm just going to subtract both sides. So we're going to be left with 2u dash of x multiplied by g of t is equal to negative u of x multiplied by g prime of t. Okay? Now I'm going to divide both sides by negative u of x. Negative u of x. That will cancel there. And I'm going to divide also both sides by g of t, because that will cancel there. So what we're left with is basically, we're left with 2u dash of x is equal to negative u of x is equal to g prime of t over g of t. Alright, now here is the tricky part. In order for this to be true, they have to be equal to a constant. Because no matter what x values I put in here, this function here is independent of this function. This will always be constant no matter how x changes here. And likewise, no matter how t changes here, this function won't change here. Because as you can see, this whole left-hand side is a function of x. And this whole side here is a function of t. So no matter what I put into this side, so if I put in t is 1, that's not going to affect this side here. It's going to be constant no matter what. Likewise, on the left-hand side, if I put in x is equal to 2, it's not going to change this side because this is a function of t. So what we can actually do, let's just get rid of all this. Oh, whoopsie daisy. G of t. We can say that basically both sides is equal to some constant lambda. So let's just get rid of that. And let's define lambda as just some real number. Okay, so it's any number in the positive and from positive to negative infinity, any number. And basically what we can do is basically we have two ODEs now. So ODEs are ordinary differential equations. So we can say that 2u dash of x is equal to negative u of x is equal to lambda, and we also have g prime of t over g of t is equal to lambda. Okay, so we have one equation here and two equations, second equation here. So now all we got to do is basically solve this linear differential equation and this second order differential equation here and this second order differential equation here via, well, not second order, I mean first order. Sorry, there's no second derivatives. So all we're going to do is this one first. So we're going to have 2u prime of x, and I'm going to move this negative u of x up here. So we'll have negative u of x over lambda. And now all I'm going to do is change my notation. So u prime of x is the same as the derivative of u with respect to x. And u of x is just the same as u. So replacing that, we'll have 2 du dx is equal to negative lambda u. And divide both sides by 2. Negative lambda over u. Now, we can't integrate yet because we need this variable on the bottom here. So we're going to flip both sides of these equations. So we're going to have left is dx over du is equal to 2 over lambda u. Okay? So x is equal to the integrate this side. You can take out -2 and lambda because it's a constant. The integral of u du. 1 over u. Okay, so recall that if you integrate something 1 over x dx, that's the natural log of x plus a constant, pretty much. Okay, right, so same rule here. So x is equal to -2 over lambda natural log of u plus some constant c. Now we're going to rearrange this to get off basically u by itself, because recall up here we're looking for a function, we're looking for our u, because at the start we made the assumption that our function of two variables is a function of x and a function of t. So we need to find this function here, u of x. Okay, so let's just go back down to our equation here and rearrange. Alright, so c is an arbitrary constant. So if I minus c on this side and minus c on this side, it doesn't have to, this c basically is still any constant. So we can still just put it as just plus c. It's just the plus c on this side won't, this plus c on this side will be the negative of this plus c here, just as long as you take that into account and understand what you're doing. Because if we're just moving arbitrary constants around, it doesn't really matter what sign you give it, as long as you know it's just an arbitrary constant, because c can be from positive infinity all the way to negative infinity. Okay, so c can be anywhere. Okay, so we're going to have x plus c is equal to -2 over lambda log of u. Okay, we have to keep in our lambda here, and we can't fudge that with c, because we made the assumption up here that the function of x and the function of t are equal to the same constant, pretty much. So we'll just leave, we won't combine our lambda with our c, but we will rearrange this still. So we're going to multiply, we're going to basically multiply both sides by lambda over -2. And that's going to affect that. So what we're left with is basically the natural log of u is equal to negative lambda x over 2 plus lambda c over -2. Alright, so what can we do here? Now we can recall that if we have ax is equal to b, we can rearrange this and have log of a of b is equal to x. So doing that down here, we know that the natural log is just log to the base e, and e is 2.71, it's just some number. So we'll have u is equal to e to the power of negative lambda over x over 2 plus lambda over c over -2. Now we can basically make this a bit better. We can basically change this, because our index laws say if we have a to the m plus n, that's the same as a to the m multiplied by a to the n. So likewise, if we have e to the negative lambda over x over 2 plus lambda over c over -2, that's the same as e to the negative lambda over x over 2 multiplied by e to the lambda over c over -2. And we can say this whole thing here is just some constant a. So we can simplify this as u of x is equal to some constant a, e to the negative lambda over x over 2. Okay, and that's our function of x. Okay, now we have to solve the other ODE. Okay, so let's go back up and let's solve this one here, g of t prime. So again, I'm going to change my notation. So g prime of t is just basically dg dt in terms of Leibniz notation, and then g of t is just this, it's just g. So rearranging this, we're going to have dg dt is equal to lambda g, okay? Now, we're going to have to switch the top and bottom because if we were to integrate now, we'd be integrating with respect to t. But we don't have t here, we have g. G is a function of t. So all we're going to do now is just basically switch this so we can integrate with respect to g. So we'll have dt over dg is equal to 1 over lambda multiplied by 1 over g. Integrate both sides, then we'll have t is equal to 1 over lambda, the integral of 1 over g dg. So therefore t is equal to 1 over lambda, natural log of g plus some, oopsie daisy, plus some arbitrary constant. Okay. Now, I'm going to rearrange this without explaining myself because I explained myself down there with the function of x. So this whole thing is going to be g of t is equal to e to the lambda t, and then you have a constant here, a prime. Alright, so what does this mean? Alright, so now we have our two functions. So we have a function of g and a function of u. So we have u of x is equal to some constant e to the negative lambda x over 2. Okay, and we have g of t is equal to a prime e to the lambda t. Lambda t. And at the start, we made the assumption that f of x and t, the solution to our partial differential equation, is the product of u of x and g of t. So now we just substitute those in. So we're going to have a times a prime. That's just going to be some other constant. So a times a prime, let's just say some constant b. So we're going to have b e. Since they're like bases, you can add the indices. We're going to have basically negative lambda over x over 2 plus lambda over t. And that is our solution to our partial differential equation up here. Alright, so that was basically a follow-up video. I've made a video on the channel. I'm solving one of these before, but this is how the solution down there to this partial differential equation. I will be making like 2 more videos on this topic. If you have any questions, leave some in the comments. If you enjoyed and learned something, thank you. And just, yeah. Alright, see ya.